So, good morning, guys. Welcome to NEET World Institute and NEET World YouTube channel. So, in this class, we are going to concentrate on this convection and radiation. So, in last class, we have done n number of problems like last two class, right now, thermal properties of matter like thermal conductivity have done, and under conduction we have done many problems, thermal stress we have done, right now. So in this class we will start with convection and radiation topics, and we'll see some more problems. Okay, so we'll wait for 1 or 2 minutes and the people are joining over here. Okay, yeah guys. So can we start now? So we are seeing this process. I guess we need to start with this convection, right? Convection we need to start right now. Okay, I guess the people have joined. We can start over. Okay, so guys, conduction we have seen like there is no motion of the particle right now, but whereas convection, if you see, convection is a mode of heat transfer by actual motion of the particle or actual motion of the matter. We will talk, right? So convection is a possible only in fluids. Fluids means nothing but yeah, so it's actual motion we will talk, and fluids is nothing but liquid and gases we will say right now. So convection involves bulk transport of different parts of the fluids. So convection can be a natural convection and the forced convection, like two types of convection, right? So the main important point is it's actual motion of the particle or matter, and it's applicable in liquid and gases. Why? Like even when we talk about a solid, yes, we can say, but especially we are talking about liquid and the gas particle, that is the fluid parts. Okay, and when we go for the next one, so sea breeze, like is the example, simple example. So during day the ground heats up more quickly than water, and air over the land is warmer than the air over the water. Okay, and it's vice versa, like during day is like this and during night it will be vice versa. Okay, and yeah, radiation we will talk of. So the meaning of radiation is nothing but it's a process of transmission of heat without affecting the inverting medium. So there is no a medium between them, like thermal radiation, electromagnetic radiation emitted by a body by virtue of its temperature. So properties, if you see, they travels in a straight line. First thing, they travels with a speed of light. Third one is they undergo a reflection, refraction and interference. Okay, because we are talking about a straight line and light, na, so reflection, refraction and interference will be there. and if you talk about, they obey inverse square law. Okay, and thermal radiation falls on other bodies like it's partially reflected and partially absorbed. Okay, this is the main thing, like heat without affecting the inverting medium, and it is travel in a straight line. Wait, where it went? So straight line, speed of light, reflection, reflection, refraction, and interference, and inverse square law. These are the 4 important points when we talk about the properties. Okay, when we talk about the properties, right? Yeah. So this is important thing when they are asking the theoretical part question based on the radiation. So universal emission and electromagnetic wave, travels in vacuum, speed and path, temperature dependence, wavelength shift, light like behavior, and inverse square law. Okay, so first one, if you see the first one, no, wait a minute. I guess it's clear now. Okay, if you see the first one, universal emission, all objects with temperature above absolute zero constantly emit the thermal radiation we are talking. And electromagnetic radiation, electromagnetic wave, so radiation is a form of electromagnetic wave, that is EM waves, we will say, no, like light or radio waves. We are talking about the light, it travels in the properties of a light, so it's a straight line, we are saying straight line, and travels in vacuum because it's an electromagnetic wave, right? It does not require any medium like air, and can travel through a vacuum also, like empty space also. So which is how the sun reaches the earth. It's like a vacuum thing, right? And the speed and the path, it travels at the speed of a light, so 3 into 10 power 8 right now, and moves in a straight line. So temperature dependence, hotter object emit far more radiation than the cooler object. Obviously hotter object emits more, and wavelength shift is nothing but as a temperature increases, right? As the temperature increases, the peak radiation shift from the longer wavelength to the shorter. If temperature increases, let me take if temperature increases, wavelength shift to like the longer to shorter. Okay, when temperature decreases, vice versa of this. Okay, and light behavior, light like behaviors, it obeys the law of optics, like whatever we have seen in the optics, right? So it's the main thing we are observing here: reflection, refraction, and interference. And when we talk about the inverse square law, it is inversely proportional to the r square, the distance r square. Okay, so these are the thermal properties, properties of radiation. Okay, properties of thermal radiation we are talking. Got it? So the next one, yeah. So when we talk about a body, like absorbing, absorption, reflection, and emission. So the sum of, if I add everything, reflection, absorption, and radiation, I'll get the total heat. Okay, when a radiation, that is heat energy, is a form of wave, falls on a body, 3 things can happen. One is absorption, one is reflection, one is an emission, right? Yeah. So Q is nothing but the incident or total radiation, that Q, and R is nothing but a radiation. T is nothing but transmitted radiation, like reflected radiation, transmitted, and absorbed radiation. Reflected radiation, transmitted radiation, and the absorbed radiation, right? So when we talk about, if we divide by Q everything, we will get like QR plus QT plus QA will be equals to Q. So Q will get cancelled. 1 will be equals to R plus T plus A. That's the value we have got here. So reflecting power, transmitting power, and absorption power, the thing we have written here. Okay, So A, which is nothing but QA by Q, R, which is nothing but QR by R. So R is nothing but reflecting power, A is nothing but absorbing power, T is equals to QT by T. Okay, so QT by Q. Okay, this is transmitting power. So this is one of the important formula you can note. You can take a point of this, right? I guess you have noted down the things, right? I'll give a simple tabular column to observe carefully. So type of a body: perfectly black body, perfect reflector, and perfect transmitter. Okay, so reflecting power, transmitting power, absorption power. If you take a box and if you draw perfectly, perfectly black body, what means it absorb everything, which means 1 remaining to 0. Perfectly reflector, so reflect everything, 1 0 0. Perfectly transmitter, 0 1 0. Got it? Take a note of this and we can go for the next point. So this, if you understand this table, if you keep remembering the table, it is easy, right? You can take a note of this. I guess done. Okay guys, now we'll see the next thing. So absorption power, emissive power and emissivity, it's an important formula. So absorptive power is nothing but it tells us how much radiation of a body absorbs, which means A is nothing but energy absorbed by energy incident. Okay, and for a black body radiation, A is nothing but 1. So emissive power, heat energy transmit radiated per unit area, is called as emissive power, unit area per unit time. Okay, so E is equals to Q by delta A into delta T. And unlike absorptive power, emissive power has units. Fine. So emissivity is nothing but emissive power of a body at a temperature T divided by the emissive power of a black body at the temperature T. So remember carefully, emissive power of a body at temperature T, emissive power of a black body with respect to black body we are talking. So E by E naught, E by E naught. So E, I will take it as it is, E naught for the black body. So for a black body, emissivity is nothing but 1, and real object emissivity is less than 1. So this is important formulas which we are taking in the radiation parts, and we'll see some more formulas and the problematic points. Okay, take a note of this. Done. Okay, yeah. So Kirchhoff laws of radiation. So good absorbers are good emitters. So Kirchhoff stated that so emissive body divided by the absorptive body, like the ratio of this. So emissive by absorb is equals to the black body. So meaning is nothing but if a body absorb radiation well, it also emit radiation high. So if absorb high, emissivity also will be high. Okay, so I mean radiation absorption is high means radiation also will be high. And a black body is a best absorber and best emitter, a black body. Okay, and so the surface which are dull and black, good absorber, which are dull and black. Okay, shiny or white surface, bad absorber. That's the thing. People are used to say that don't wear black shirts. This is the reason. Okay. So when we are using this black shirts or dark shirts, the absorption power will be greater, and when we are using the light, so the absorption power will be less. Okay, and the next thing is black body radiation. So an object that absorbs all radiation falling on it, and at all wavelengths, so absorption absorbs every radiation and in all wavelength is called as black body at uniform temperature. Its emission is called as black body radiation. Fine. So Wien's displacement is nothing but a black body radiation curve for different temperature peaks at a wavelength inversely proportional to the temperature. So when we talk about wavelength is always inversely proportional to temperature. We have discussed, right? So when a wavelength increases, temperature decreases. Like if temperature decreases, only wavelength increases. No, and the temperature increases, wavelength also decreases. So what they're saying, wavelength is inversely proportional to temperature. Wavelength into temperature is equals to constant. That's the meaning. Okay, to remove that constant is nothing but Wien's constant B. So the value is nothing but 2.9 into 10 power minus 3, approximately 3 into 10 power minus 3. Okay, so this is the Wien's displacement law. Fine. So the next one is the main points. When the temperature increases, the object emits more energy. Okay, temperature increases, objects emit more energy. Energy is not emitted equally at all wavelengths. So if wavelengths varies, energy also varies. Third point is for every temperature there is one wavelength at which emission is maximum. Okay, and if the temperature increases, the wavelength at which maximum energy is emitted becomes shorter. Maximum energy is emitted becomes shorter. These are the four important points, right? And Stefan-Boltzmann's law. So Wien's displacement we have seen. This is Stefan-Boltzmann's law. The total radiant heat energy emitted from a surface is proportional to the fourth power of the absolute temperature. The total radiant heat energy from a surface is proportional to the fourth power of the absolute temperature. Okay, so depends upon the area also. So H is equals to A sigma T. But what is sigma? Sigma is nothing but that Stefan-Boltzmann constant, which is nothing but 5.67 into 8 10 power minus 8. 5.67 into 10 power minus 8. Okay, so this is Stephen-Boltzmann's law. And for other perfect radiator, no, we will add the value of E, which is nothing but emissivity. So for normal body, we will take A sigma T power 4. For other perfect radiator, A E sigma T power 4. Only the E value we will add, and where E is nothing but emissivity. So it depends on nature of the material too, because we are talking about the perfectly radiator, na? Like so different from different objects, right? So that's why. Got it? So next one, a body at temperature T, surrounding temperature, okay, that is Ts, emits or receives energy. Okay, so for when we talk about the different temperature, the temperature of a body and surrounding temperature, we will talk about the a change in temperature, T power 4 minus Ts power 4, like change in temperature, like temperature of a body to the surrounding temperature. And for a body which is emissivity is E, the similarly St is equals to Ae sigma T power 4 minus Ts power 4, temperature of a body power 4 minus temperature of a surrounding power 4. Got it? Yeah, you can take a note of this and we can go for the next one. Done. So greenhouse effect, yeah. So a large portion of radiation is observed. A large portion of radiation is observed by gas like carbon dioxide, methane, then nitrous oxide, then chlorofluorocarbon and ozone. Okay. So heat up at atmosphere resolving in warmer surface at Earth. Warmer surface at Earth. So without greenhouse effect, temperature of Earth would be minus 18 degrees Celsius. Minus 18 degrees Celsius because of the greenhouse effect. Like the everything is controlled. Okay, and Newton's law of cooling. It's one of the important point. Okay, the rate of loss of heat. In the sense Q dQ by dt of a body is directly proportional to the difference of temperature delta T of a body and its surrounding. Okay. So minus dq by dt is directly proportional to delta t. To remove the proportionality, we are adding a constant called k. So why negative sign? So rate of loss of heat, no, the negative sign indicates the loss of heat with time. So minus dq by dt is equals to k into t2 minus t1. The amount of heat lost, dq is nothing but ms delta t, no, ms delta t. The same thing we will write here, ms delta, dt by dt. Got it? So take t terms one side and remaining term other side. Fine. So dt by t2 minus t1, and if I take this k divided by ms into dt, k divided by ms into dt. So we will get the formula as t2 is equals to t1 plus c dash e power minus kt. T2 is equals to t1, t2 minus t1, like change in temperature is equals to c dash power, so c dash e power minus kt. Okay. So it's a constant, C is a constant. Got it? So this law holds good only for small different temperature. It's not for a long, like a big temperature and all. So the law the laws of heat by radiation depends on the nature of the surface and the area of the exploded area, exposed area, surface or exposed surface. Got it? And yeah, limitations if we'll see, and we'll go for the problems. So valid only for small temperature difference. Applicable mainly when heat transfer is by convection, only for convection. Okay, if conduction is there, no. Surrounding temperature must remain constant. Surface of a body should be uniform, not accurate for very long time intervals, does not consider effect of air movement. Okay, so these are the things of the limitations. Okay, so with this we'll conclude this convection and radiation of the class, today's class, and we'll continue with the problematic session in the upcoming session. Okay, so thank you guys, we'll meet in the next class. Bye bye.